In today's video, I'm going to be looking at the sieve of Erastothenes, which is a way to quickly find the prime numbers in a given set. So in my case here, I'm going to be considering a situation where all the numbers are present, but ideally it should work for any set of numbers. For our example, I'm going to be getting the set of numbers from 2 to 20. This is important because for the numbers 0 and 1, we cannot compare these two. They cannot be considered prime numbers for the purposes of this sieve. However, if you do have them in the code, you need to consider that as an edge condition. Okay, so this is how we go about it. We are in effect going to be using 2 pointers here. So pointer I and pointer J. Pointer I will put at the first number that we have in our set. In this case, the number is 2, and pointer J will put at all the multiples of 2 or of that number. So when we start out the iteration, we'll start with pointer A going at 2, and then pointer J is going to iterate. That means it will go to pointer 4, 6, 8, 10, 12, 14, 16, 18, and 20. So these are the numbers that are multiples of J. Now what we want to do is we want to remove all those numbers because we know for sure that they are not prime since they are multiple of that first number. So in this stage, as you can see, I have gone ahead and deleted them from our set, and now we have the numbers that have remained. Now that we have managed to get rid of all the multiples of 2, we can now move the pointer I to the next available number. So that number is 3. The pointer J again moves to all multiples of 3. So the multiples of 3 that remains at this point in time are just 9 and 15. So that's where J is going to be. So at this point in time, we repeat that same procedure where we now remove all the multiples of 3 that we have, and now our value or our set is less all of those numbers. So that gives us a solution, and we do not need to proceed. As you can see, that's the set of numbers of unique numbers as highlighted here. There's really no point in going above 5, and you can actually prove that mathematically, and I will show that in the next slide. For now, what is important to understand is that you only need to move the pointer I to the square root of n. That's the maximum number that it will always be. That means that the time complexity of this algorithm is going to be O of n log of the log of n. And the space complexity, if we use this algorithm, is going to be O of 1 because we don't create any new structures. However, if you do want to create a new structure that's going to keep track of all the primes, then that might move this to be an O of n space complexity, as we need to create a new structure holding this. Okay, so maybe I think it's good to try and understand why we don't need to go past the square root of n. So let's imagine there was a composite number, and that number existed between the square root of n and n. If such a number exists, that means that its composites, let's give it some arbitrary values, p and q, would either be both be before square root of n, both be after square root of n, or be distributed between those two. So if they are both before the square root of n, then they would be covered using the ordinary procedures of the sieve of Erastothenes. If, however, they are both after the square root of n, then that will give a number that is greater than n, which means that such a value cannot exist. So the other way is that if we have this composite number having factors q and p such that q is before the square root of n and p is after the square root of n. So now getting here, we know that the number p must be a prime number. The reason for that is if p was a composite number, then we could go through the same operation and be able to split it and have one of its factors be below the square root of n. If that did happen, that means that p would also have gotten cancelled out. So that tells us that p must be a prime number. In this way, we can show that there cannot be prime numbers after the square root of n if we have been, sorry, there cannot be composite numbers after the square root of n if you have been running the algorithm of the sieve of Erastothenes. So in my case here, this is how to show you a potential implementation that will work for smaller numbers of n. Now we start by finding the end value, which is really finding where the square root of n would lie. We want to go at least one index above that. Then of course we use I, the index I, to go from the beginning to the end of that, to the end that you have just determined. And then after that, I'd take in, if I'm just using 0 to mark, so if a number is found to be a composite, I'm just going to zero it out. Then after that, I use j to go through all multiples of I that are there. Whenever I find that multiple, I am going to actually go ahead and set that to 0. And then after that, I'm using the characteristics of a set to remove all the zeros that were set in that number. What I should mention is that this algorithm is going to work only under specific circumstances, and that is where all the numbers are included in this particular num set, and they are all in order. So that's some of the things that we need to take care of that. And then this also assumes that the number starts from a 2 to the number n, whatever n is, be that can be arbitrarily. So the assumptions that are made here. There are multiple ways of improving this algorithm, but I just wanted to put it in this way so that you can understand the reasoning behind it.